You ever get that feeling like some problems, they seem impossible at first,
Yeah.
but like
Yeah.
if you just shift your perspective a little bit,
Right.
the solution, it becomes clear.
Absolutely. It's really interesting how often the answer
Hmm.
lies in like those spaces that you just don't think to look at first.
Yeah, and that's where this whole world of linear
Yeah.
algebra comes in, right?
Yeah.
So these concepts of rank
Yeah.
null spaces, and then there's all this like hidden like geometry in
Right.
there. It's really cool.
Yeah, it all starts with matrices.
Yeah.
You know, those grids of numbers that we see all the time.
Right? Yeah.
But they're more than just tables of data.
Hmm.
They're really powerful tools that represent these things called linear transformations.
So we shouldn't think of them as like static grids. We should think of them as like
Hmm.
dynamic processes,
Yeah.
like almost like recipes that transform ingredients,
Right.
which in this case are vectors, into something new.
Exactly. Yeah, and just like a recipe, if you understand the matrix, you can kind of predict what kind of dish you're going to end up with.
Okay.
You can even figure out which combinations of ingredients might lead to the same result.
So we've got these matrices acting as transformation recipes.
Yeah.
Where does rank fit into all this?
So the rank of a matrix tells us how much real information a transformation can generate. So it's all about the number of truly independent directions the transformation can create. Think of it like, stretching or rotating a shape.
Hmm.
The rank determines how much freedom of movement you've got.
So a higher rank means more flexibility,
In a sense,
more
yeah.
ways to manipulate the vectors.
A higher rank means a richer transformation, one that can take vectors into a more diverse set of outputs. And this concept of rank is directly tied to the dimension of the spaces spanned by the matrix's rows and columns. Interestingly, both row and column spaces end up having the same dimension.
Okay, now what about those matrices with like a lower rank? Do they have less transformative power?
They do. They operate in a more constrained space. And it's like working with a recipe that has fewer ingredients. You might end up with some unexpected results.
Okay.
They introduce a degree of flexibility, but sometimes also ambiguity.
Okay, this brings us to the null space.
Okay.
This sounds kind of mysterious.
It might sound mysterious, but it's actually quite intuitive. The null space of a matrix is simply the set of all vectors that get squashed down to zero by the transformation. They disappear, essentially becoming invisible to the matrix.
So it's like finding those combinations of ingredients that result in no output whatsoever.
Exactly.
Okay.
And this seemingly empty space actually holds valuable information.
Oh, interesting.
It reveals the structure of the transformation
Yeah.
and helps us understand which input vectors are redundant or irrelevant to the process.
It's like discovering a hidden room in our matrix house.
Right.
That tells us something about the architecture of the whole structure.
And this hidden room, the null space, has a fascinating relationship with the rank. They're connected through something called the rank nullity theorem.
So there's a balance between how much information a matrix can generate,
Right.
its rank, and how much it makes disappear, its nullity.
Precisely. As the rank increases, meaning the matrix has more transformative power, the null space shrinks. Fewer vectors get mapped to zero because the transformation is spreading its influence wider.
Okay, that makes sense. So if a matrix has like full rank, it's like a super efficient machine
Yeah.
transforming everything in its path. Nothing gets lost in the null space.
And in those cases, especially with square matrices, the matrix becomes invertible. It's like having a recipe where you can reverse the steps and get back to your original ingredients.
Okay, so we've got this intricate dance between rank and nullity, revealing how a matrix manipulates information. But there's more to the story, right?
Right.
We hinted at some hidden geometry.
Right. And this is where it gets really interesting. The row space of a matrix, which represents all possible combinations of its rows, and the null space, the set of vectors that vanish under the transformation, have a unique relationship. They're actually perpendicular to each other.
Wait, so we're talking about geometric relationships
Yeah.
within a matrix?
Yeah.
That's blowing my mind a little bit.
It's like having a room where the floor represents the row space, and all the directions pointing straight up represent the null space. They exist in the same space, yet are completely orthogonal to each other.
So each vector in the null space is at a right angle to every single row of the matrix.
Exactly. And any linear combination of those rows, which forms the row space, would also be orthogonal to the null space. It's a fundamental geometric relationship that helps us understand the deeper structure of linear transformations.
It's like discovering a hidden blueprint that guides how the matrix operates, revealing a beautiful order within this world of numbers.
And this connection between the row space and the null space goes beyond just theoretical elegance. It has profound implications for understanding how we solve equations, analyze data, and even design algorithms.
I'm starting to see how these concepts aren't just abstract mathematical curiosities. They hold the key to unlocking a deeper understanding of information itself.
Absolutely, it's true. These concepts provide a powerful lens for understanding and manipulating information in a wide range of fields.
So let's dive a bit deeper into why this matters.
Okay.
How does understanding this interplay of rank and null spaces and perpendicularity help us in practical terms?
Imagine you're trying to solve a system of linear equations.
Right.
The rank tells you whether you have enough independent equations to even find a solution, and if so, how many solutions there might be.
So it's like having a map that tells you whether you're on the right track to finding your destination.
Right.
And how many different routes you might be able to take.
And the null space provides a detailed guide to those routes.
Okay.
It describes the structure of all possible solutions, revealing the degrees of freedom you have in finding an answer.
It's like having a key that unlocks a hidden door, revealing a whole room full of potential solutions.
Exactly. And this understanding becomes crucial in fields like machine learning.
Okay.
Let's say you're training a model to recognize patterns in data. The rank of the matrix representing your data can tell you whether you have enough diverse information to train the model effectively.
So a higher rank means a richer data set capable of capturing more complexity and variation.
In essence, yes.
Okay.
A higher rank indicates that your data spans a larger dimensional space, which is essential for building robust and accurate models.
And what about the null space in machine learning? Does it play a role there as well?
Absolutely. The null space can help identify features or combinations of features that are irrelevant to the learning task.
Okay.
These are the features that when fed into your model, they don't contribute to the output. Almost like noise in the system.
So by understanding the null space, we can streamline our data, focusing on the information that truly matters. It's like filtering out the distractions to get a clearer picture.
Precisely. And this can lead to more efficient and accurate models.
We've talked a lot about the abstract concepts, but I'm starting to see how they translate into real-world applications. It's like seeing a bridge between theory and practice.
That's the beauty of linear algebra. It provides a powerful framework for understanding complex systems and making sense of vast amounts of data.
And what about this perpendicularity idea? How does understanding that relationship between the row space and the null space help us in practice?
Think about an application like data compression.
Okay.
We often want to represent complex data in a more compact way without losing essential information.
Right, like shrinking a large file without sacrificing too much quality.
Exactly. The row space of a matrix captures the essential information in the data, while the null space represents their redundant or irrelevant parts.
So by understanding how these spaces relate to each other, we can essentially separate the signal from the noise.
Precisely. We can project the data onto the row space, effectively filtering out the irrelevant information contained in the null space. This idea is fundamental to many compression algorithms.
It's fascinating how these seemingly abstract concepts have such tangible applications. It's like we're uncovering a hidden language that speaks to the underlying structure of information itself.
And this language is becoming increasingly important for everyone to understand, not just mathematicians. As we enter an age where data is everything, having a basic grasp of these ideas is crucial.
It feels like we've been given a set of tools to navigate this data-driven world, to make sense of the patterns and connections that might otherwise remain hidden. So we've seen how these concepts from linear algebra can help us understand and manipulate data in a variety of ways.
Yeah.
But I'm curious to explore some specific examples of where these ideas really shine.
One powerful application lies in the field of machine learning.
Okay.
A fundamental algorithm called principal component analysis, or PCA, relies heavily on these concepts.
I've heard of PCA.
Oh, okay.
It's all about simplifying complex data sets, right? Finding ways to represent data in a lower dimensional space without losing too much information.
Exactly. And at the heart of PCA are these special vectors called eigenvectors and their corresponding eigenvalues. They play a crucial role in identifying the most important directions in the data.
Okay, let's talk about eigenvectors and eigenvalues. For a moment, I remember them being a bit tricky to wrap my head around.
Imagine applying a transformation using a matrix, and you notice certain vectors don't change their direction. They simply get stretched or compressed by a certain factor. Those special vectors are the eigenvectors, and the scaling factor is the eigenvalue.
So they're like the stable directions in the
Right.
data. The ones that resist being twisted or turned by the transformation.
A good way to think about it. And PCA leverages these stable directions to identify the principal components,
Okay.
which are the directions of greatest variance in the data.
So by focusing on those principal components, we can essentially capture the most important features of the data while reducing its complexity.
Precisely. It's like finding the essence of the data, the core elements that carry the most information. This is how PCA helps us simplify data sets for visualization, analysis, and even for building more efficient machine learning models.
It's amazing to see how these concepts, which might seem abstract at first, can have such profound implications for understanding and manipulating data in practical ways.
And these ideas extend beyond machine learning as well.
Okay.
Consider the problem of solving systems of linear equations. Remember how we talked about the rank of a matrix telling us whether a solution exists and how many solutions there might be?
Right. It's like having a roadmap that tells us whether we can reach our destination and how many different paths we might be able to take.
Exactly. And when we encounter an underdetermined system where we have more unknowns than equations, the null space comes into play. It helps us characterize the entire set of possible solutions.
So instead of just finding a single solution, we can explore the entire landscape of possibilities, understanding the degrees of freedom we have in choosing an answer.
Precisely. This has applications in fields like control theory, optimization, and even in understanding physical systems with multiple degrees of freedom.
It's incredible how these seemingly abstract concepts of rank, null spaces, and perpendicularity weave their way into so many different areas of science, engineering, and even everyday life. It's like we've uncovered a hidden language that speaks to the underlying structure of information itself.
And the more we explore this language, the more we appreciate its elegance and its power to unlock a deeper understanding of the world around us.
It feels like we've been given a new set of lenses to view the world, to see the patterns and connections that might otherwise remain hidden.
So keep exploring, keep questioning, and keep pushing the boundaries of your understanding. The journey into the world of linear algebra is full of surprises and insights.
It's been a fascinating dive into the world of linear algebra. Thanks for joining us.